Hello, everyone. Welcome to those here with us in Cambridge and joining remotely. Really pleased to have ZQ Liu giving this presentation. It's been fun hosting him for a few months here in Cambridge, and we've had a lot of really interesting discussions. So looking forward to his talk, and thanks a lot for being willing to give it.
Okay. Thank you, Chuck. Thank you, Chris, for having me here in Cambridge. It's a lovely place. I met a lot of people, like my former student, Jack from Penn State, and it's fun. I really enjoyed a lot. Today I'm going to talk about a title. My talk is Zentropy, and I know that some of you will wonder what Zentropy is about. And I tell you that I didn't know that either 1 year ago. So we got a new name just about a year old today. So Zentropy is two words, actually, Z plus entropy. Z, we know what Z is, right? Z is a German word for a partition function. It's used as sum. Basically means you have all the states, sum of states together. That's Z, which we use all the time for partition function. Okay. Entropy, all know that too. Entropy drives all changes in every system. Anything is driven by entropy change. That's second law of thermodynamics. So if you think about the Z and entropy put together will be Zentropy. It's really that we kind of calculate the total entropy in a system, starting from electrons to whatever the states you have. We do this through microstates. I mean, it's kind of configurations. In the other term, we start with ground state. That's quantum mechanics. We can do, then we'll go up to long ground states and put them together. You hear okay? So as I mentioned, this term I started last year. I gave a talk, I gave a virtual talk last year in June about entropy. That title was Entropy. It was at Z. I was talking about I need a term for the approach. So we're trying to figure out what term to use with a partition function, superposition, and different method. And then one person said, this Josh Robert, he said, oh, you should call it a Zentropy. Basically, partition function of entropy. Okay, that's we got a term. So we have been using that term since last year. There are 2 papers we published this year. There's a couple more come up already accepted. I will mention one of them is that we started to use the term because we found it really represents what we do or the method does. So this is our first. Then we started this work actually back in 2008. We found some challenges in the simulation, and then we developed a method to do cerium. Okay, cerium is one of very interesting elements. Actually, it's the own element on periodic table, which is non-magnetic at 0 Kelvin. When temperature goes up, becomes magnetic. That's the only one element in the whole periodic table that does that. So it's very unique. That has been studied a lot. Try to calculate the phase equilibrium. The transition, particularly the isostructure transition between the FCC, which is non-magnetic, and the ferromagnetic. So we did that in 2008. As you can see, we're punching PRB, and we did 2 states. We take the ground state and one long ground state, which is ferromagnetic. We found that doesn't work. It didn't work out well. So we had to add a mean field term, which is for the spin fluctuation. So it worked well. Then in 1 year later, we found that maybe we should add 2 states. So we take the non-magnetic state, that's ground state. Then we take the ferromagnetic state, the high temperature state. And then we say between the 2, there must be more states. So we add 1 AFM, anti-ferromagnetic state. We get 3 states. Then it worked very nicely without the mean field model. Then we went one further to calculate this IMA alloy, which is we use iron 3 platinum instead of iron 3 nickel, because nickel is more complex in calculation. So we turned out it turned out working very nice. This time we have way more states. We have 2 to the 9th power of this iron spin configurations. Okay, if you do symmetry analysis, and there are only 39 of them, 37 of them are unique, but you have all taken 5-time curve. Okay, so what's the purpose of doing that? Is that we do modeling. I'm a modeler. I do thermodynamic modeling for many years to model the free energy function of a system, of a phase. So in the modeling work, you first have to define a model. You can use the Bragg-Williams model or whatever model you put in there. Then you have to truncate it. because you cannot take everything into consideration, truncate it, and then you feed the model parameters. Either you see experiment data most of the time, or use DFT data, and you get a model. Then you do the application, which you do interpolation and extrapolation. That basically does the modeling side. Of course, now we have quantum mechanics. We want to predict them, right? Prediction, but we really want to put the microscopic properties which we measure, but we don't want to experimental input. Right? We want to predict completely from the theory. So that's one of the key challenges in science. If you go to the Department of Energy, they send us a program every year. Can we predict the microscopic properties without experiment data? That's really one of the big effort. And the reason is because when you do experiments, you measure more than one state. It's a mixture of all states because temperature at high temperature activates different states. So it's really a mixture of ground and non-ground states. Okay, but in DFT, most time we'll focus on the ground state. Of course, nowadays we do beyond that. For example, you can do effective Hamiltonian. You can put different information together, or you can coarse grain the DFT. It's very popular. A lot of papers published in the last 10 years. So you can put different states together. But still, you have to have a model, and then feed the model parameters. Then you said you want to do simulation. You can put a cover as a hybrid model. Is that we have fringe model models. Then we take a DFT data, feed in the parameters. We find that we never reproduce experiment, so we find the parameters. Okay, so do that. So the question is that what the solution would be. So we know that we have different states. It's based statistical, right? Is statistic mechanics. Okay, so that problem should be solved already. So why it's not solved? I'm going to mention that. And the first one is not solved is because we could not get all the microstates from theory. Experiment measurement have much more states than we can measure. Then we can predict. That basically we have a lot of internal diffuse freedom of the system. The first one. And the second one is that when we calculate the properties, most of the publications calculate 0K. Okay, so you did not calculate free energy. They calculate 0K. Of course, now we can do it. Take that one. But then the third one is the most interesting one, which we think is a contribution from Zentropy, is how to put them back together statistically. Okay, I think that's what Zentropy is about. That you calculate all states. You got the energy, you got the free energy. How to put them back together? Okay, that's what we call the statistical mechanics to do that. Okay, so now let's talk about the properties. What kind of properties we mean by the microscopic properties? And the blue, no, the yellow ones are I call the potentials: temperature, stress, electrical field, magnetic field, and the chemical potentials. And the white ones here and in the column are the properties you measure, right? You measure entropy, you measure strain, you measure dielectrical displacement, the magnetic induction, and the moles you measure. So this relation between two sets of quantities are first derivative of the free energy. So if the Helmholtz energy derivative to temperature gives entropy, right, as first derivative, the two sets of quantities. And then in the middle of the table are the second derivatives of the free energy, which is the first derivative of the white parameters, white quantities to the yellow quantity. For example, entropy to temperature derivative gives you heat capacity. That's the first derivative, but the second derivative of the free energy. Okay. So all of them are second derivative. That's the properties we talk about most of the time when we do measurements. Okay, for example, you change stress, you measure how strain, right, and how the electrical property changes, or how the magnetic property changes. But actually, it's interesting. When you change stress, how about the mole change, right? That's actually interesting quantity. That's why these quantities here are blue. It's not in the red or black. So I have three colors here for different quantities. The red one, that between we call the conjugated variables, TS, as one set of parameters that come together, go to free energy. So the red parameters are always positive in any system, stable ones. But the black ones, they are also the second derivatives, but they are not the conjugated variable between conjugated variables. So they can be either positive or negative, because our laws did not say they must be positive or negative. Then they change sign when it depends on condition. Then the blue ones are the new quantities, which we found actually very important when we talk about the quantum criticality, for example. So the mass, think about this one, right? The mass can diverge with respect to temperature. The mass can diverge with respect to stress, and diverge with all the quantities you can control. That's actually very interesting. This table is symmetric based on Maxwell relation. Maxwell, of course, is from Cambridge. Yeah, Maxwell relation. Okay, this is I call it MP1. This is between the white quantity and the yellow quantity, between the molar quantity of the potentials. However, another quantity which we found very interesting is I call it MP2. It's between two potentials. For example, of course, between temperature to temperature, there'll be one, right? Yeah, the diagonal term is one. But how about the temperature to stress the temperature? That means you change temperature, stress become different, right? How is it affected? This set of quantities actually are very, very interesting. Turned out it's related to what Onsager called a cross phenomena. If you remember, if you know the Onsager relation, he mentioned that the matrix should be symmetric, and turned out I have some different opinion than that one, so I wrote a paper on that, and which introduces a new set of quantities between two potentials. I turned out very, very useful. I point one of them is that this is this electromechanical reaction, right? So if you change stress, generate electricity. Okay, so that's the ferroelectric material does that. Or you talk about if the electron potential changes from the temperature, that will be the thermoelectric property, the Seebeck coefficient. So it's a very diversity of this MP2 different properties. So as I mentioned, this property should be predicted by statistic mechanics. So let's look at the statistic mechanics. So of course, we have all learned the statistic mechanics. It says that the partition function of a system for a canonical ensemble, you get a homogeneity of a system, and then you get the individual configurations or macrostates, I call it. So the relation here is that Z equal to summation of ZK, and ZK is equal to summation, ZK is equal to exponential of the total energy, that's very important, total energy of that state divided by KBT. So that's the one we learned. So if you continue this one, then it's okay, let's calculate the free energy of probability of different state. That'll be ZK over Z. So then you see that'll be exponential of EK KBT divided by F divided by KBT. And you can calculate the total F will be weighted sum of the EK, the total energy of each microstate, and then you have the probability of a PK log of PK for different microstates. And if you go one step further, you get the entropy. Entropy of the system is equal to KB minus KB PK log PK summation. So that's basically standard statistical mechanics, which Nanda showed in his book in the 1930s, 40s. So we use this all the time, all the textbook and all the publications. So let's analyze this set of equations. So suppose we have only one state of the system. Okay. If it's only one state, then we know that F equal to UK, but we know that F equal to UK minus TSK. That means SK must equal to 0, right? So that means in this standard statistic mechanics, SK equal to 0. That means all the microstates, they have 0 entropy. That means each state only have one stage, right? So one state, that means we know it's called a pure quantum state. I call it PQS. That means standard statistical mechanics apply to the mixture of states, which those states must be pure quantum states. Okay. So for example, a lot of quantum computing are doing that. So you do one pure quantum state, you do a lot of them, and then sum up, calculate the energy of the system. That's a quantum computing. A lot of work on doing that. So it's only applied to the very simple systems. Very simple systems. Now for the real system, it's not a pure quantum state. So you have too many quantum states for real systems. That's approach. So that's why we effectively many body Hamiltonian, cause going to DFT. And when you do that, we have to do additional fitting. You have a model, you fit it. Then as soon as you start fit it, you lose a lot of predictive power of that tool. Okay. The question we think is, can we do it without fitting? Can we finish the DFT calculations, for example, then we can just predict all the properties. So that was really the question we had back many years ago, more than 15 years ago now. Can we predict it without additional fitting process. Because every time you fit, you have to know what you want, right? And then that's lose the predictive power. Okay, so let's of course come back to density function theory. As many of you know that density function was developed in 1964 with the exact theory of many body system with many body electrons. And then in 1965, have the exchange correlation functional of electron density. The central idea is that for any system, you have a ground state. If you figure system, it has a ground state. Okay. And it has a very unique electron density. So for the ground state, you have a well defined, maybe you do not know, but you do calculations to find that out. Of course, a number of approximations for that too during that process. But we know that temperature equal to 0 Kelvin. I put it as approximately equal to 0 because today we believe that entropy is not equal to exactly 0 Kelvin. But we cannot do experimental measurements because we cannot reach 0 Kelvin. But I know Ts equal to 0. T times S equal to 0. That means there's no contribution to the energy of the system at 0 Kelvin. But now if you increase temperature for that ground state, and then we know that at least two contributions. The first one would be electronic contribution. You have distribution of electrons, and you have vibrational contribution. That together is larger than 0. Okay. And then Ts is less than 0. That means it's no longer a pure quantum state, the ground state. Okay, if the ground state is not a pure quantum state, that means we cannot use the particular statistic mechanics before anymore, right? But people still use it. You look at today's publication, everybody uses the same equation for non a pure quantum states. Okay, so now of course, in addition to ground state, we can do the non-ground state, which is excited state. Yeah, but it's a specific state or specific states, each with a unique electron density. And then you can sample all kinds of degrees of freedom in the system. You can all, well, as many as you can for the macro states, non-ground states. So you got a bunch of them. So every, of course, at different energy, right? The ground state lowest energy, any other state, you're going to increase energy up there. But each of them would also have the equal to entropy equal to 0, approximately, and the Ts equal to 0, as per sure, at 0 Kelvin. And now you're going to find out temperature, the same thing, you're going to get two contributions from electron and vibrational, so it's not equal to 0 anymore. So now you see that for those states from DFT, they don't have 0 entropy. The entropy is not 0 at the finite temperature. And they have contribution to the total energy of the system, which is not included in the statistical mechanics. Okay, now I'm going to talk about just the review what I was studying about the entropy. So if you take it thermodynamics, the first equation you saw is ds equal to dq divided by t from kind of cycle. This was very important when we derive it is for a closed system at equilibrium because all the processes we have are reversible. That's the first one. So it's for equilibrium. Now, unclosed. If the system is equilibrium but not closed, then you have to add another term, right? So if the system is not closed, you have a mass exchange. The mass, each mass has entropy. So you have to add the partial entropy into the system. Now, suppose the system is open and not equilibrium. Yeah. And then you will get another entropy. We got entropy production due to internal processes. So it turns out any system we have today, except at 0 Kelvin, has some internal process happening in the system. It always have some internal processes in the system. So if we can define those internal processes, basically we can get the different microstates. Okay. If you can think about it, what could happen, the result of that process will give you a microstate, including fluctuations. So we're fluctuating in all our systems. The fluctuation itself is actually internal processes. So if you put that together, then we find that we have to include a term in any when we deal with the finite temperature properties. Okay, so let's go to that's the change of entropy. Let's absolute entropy. We all know this equation from Boltzmann's graveyard. So as K log of W. So K is Boltzmann constant, W is the number of configurations we have. However, it's really this equation it's kind of misleading. We really should have is minus KB PK log of PK. So that equation was just showed you from Statistic Mechanics. It was actually divided by a Gibbs, American scientist. Okay, because most of science was developed in Europe. Gibbs was the one that made a huge contribution in the United States. He divided PK log PK. But if all the PKs have a similar probability, then just go back to Boltzmann equation. So that's very important, the relation between these two. So we should use this one because not the probability of the states are different. They don't equal to each other. Okay, so now we know that from quantum mechanics, we can calculate the entropy of for a given state. We can calculate the electron contribution from the Fermi-Dirac statistics. We can calculate the phonon contribution from the Bose-Einstein statistics. So we got 3 entropies here now, right? We got the 2 from DFT, 1 from the statistical. So the idea is that if we put them together, then we can compare with the experiment, hopefully. But with experiment, we do the heat capacity measurement, we do integration, we get entropy. The idea is that maybe if we can combine the first 2 together, then we can predict it and have good agreement with the experiment without information from the experiment. Okay, so let's just talk about I have 3 slides to talk about what entropy is about, how we do it. So first one, from the standard statistical mechanics for a system with different configurations, different states, microstate 1, 2, 3, and so forth. Then we know that entropy of the system is minus KB with the summation of PK log of PK, if you sample all the states. However, if each microstate has entropy itself, right? So the total entropy of the system must have that distribution among different microstates and the entropy of the microstates themselves. So that basically have 2 terms now. The first term from standard statistical mechanics, second one from the what we call Zentropy from the different microstates. They have to put them together. Of course, each microstate could be divided even further, right? To even lower scale, all the way to the quantum scale we have. That would be the electrons we have. But we cannot count all electrons, so we start with DFT. So the quantum state. They have quantum state, long quantum states, and calculate all the entropy, and they do different level up all the way to the materials, to the scale where you do experiments. So this is really a nested formula. You can go to any scale you want, basically. Any scale you want. So we are working on a number of very interesting topics. Can we go to even bigger scale? So we can predict the entropy of it. Okay, so now you put them together, and this entropy has 2 terms. One is from the individual microstate, and the second one is between the microstates. Hopefully, well, we demonstrated that it agrees with experiments a lot, very well. So you have the quantum mechanics, and then you have statistical mechanics. Then I call the last one thermodynamics, because that's how we introduce heat capacity, integration, and get entropy there. So the fluctuation of the different states. So you introduce disorder. Okay, so fluctuation of these different states in the system introduce disorder. Okay, disorder and the fluctuation start from electron level, and then you can talk about anharmonicity. You can predict anharmonicity from quasi-harmonic without knowing it. And of course, you can predict the emergent microscopic properties without knowing it. This is because the interaction with generate new properties you never know before. The extreme of this emergent property is at a critical point when the property diverges, right? That means some expansion goes to infinite, and all the properties go to infinite at the critical point. Okay, now I want to go back to make the comparison between the standard, I call it standard statistical mechanics, which is the entropy, free energy, partition function, and the probability of different states. Now, if you take the one I just discussed, then I call it Zentropy, and then now entropy is different. You get the extra term there. And if you get that term there, your friend is different. This equation I actually made change this morning, because when I visited London the last few days, and the student asked question, talk about this equation. So we know F equal to E minus TS, right? That's from the standard thermodynamics. And then we know the total energy, you could do summation over the total energy of different states, the minus TS. If we put the TS from the first equation to the third equation, we get this equation. So summation of the total energy of the system is equal to summation of the individual microstates plus this one. So you have the statisticals and the internal free energy of each microstate, or total free energy of each microstate. So now if you go back to the partition function, you find the difference now. Instead of EK, we must use FK. So partition function has to use FK instead of EK to do that. I mean, the probability is always very different. Probability is always very different. Probability now becomes FK minus F instead of EK. That makes a huge difference for the probability and for the energy of the system and the properties of the system. So we have a couple of examples we did in the last a few years. Is that we first have to make sure that we get the enough states. Your microstate has to capture the they call the ergodicity of the states. You have to sample all internal degree of freedom. And there are many literature. If we go back to the beginning of the modeling of the magnetic materials, have two states. The Weiss model has two states, right? The two states, high spin, low spin states, for example. Do that. But the two states are not enough, okay? Because they're not ergodic. Because two states come together to form a new state, which is not covered by the previous two states, okay? Because in distribution, you cannot form a statistic distribution, two states. You have to have three of them at least get distribution. So that's a very important concept, because I see publications, as also people ask question, why not two states only? Two states is not enough because you cannot cover the ergodicity of the state. And dimension too, how big the microstates? That's actually a very different question, because we are based on DFT, so it's limited by supercell, by the computing power we have. But if you do have the long range interaction, you can actually solve it by called a mixed space approach, which we developed a few years ago. All right, so now you calculate all the properties for each microstate by DFT, which we know how to do that. And then put them back to the statistic mechanics, but use the free energy. So that's basically the approach we have been doing. And we have a couple of examples. Of course, I'm not going to go through all the examples, but I'm going to show the microstates which you used. If you get the microstates, actually the calculation itself will become very trivial after that. Okay, so this is the first one worked on. I mentioned that this is cerium. Oh, actually, should be for the low one. Sorry, this is for cerium. At the beginning, we take two states: Fm, that's ferromagnetic, and Nm is non-magnetic. As the solid blue and the open red circle. I take two states. We could not predict the transition of the phase diagram. Then we add the new state between. That's the half field blue circle. So that's this one. That's AFM state. So assume at 3 states, it works beautifully. So if you think about the probability that in the middle is the non-magnetic, which has highest probability at 0 Kelvin. Another two have very low probability. One's on one side, another one on the other side. And now what is the real distribution, of course, is continuous, right? It's continuous. But if you take 3 states, actually you can predict the property very well. We have a paper on that. Then for the iron 3 platinum, we have to take a lot of more states, as we mentioned. You see, you have the ferromagnetic, you can all spin one direction, then you change some of spins and change all of them, and change different spins. You got all kinds of structures. And then we did it for BCC iron. We take a collinear magnetic configuration. Now we have 12 configurations for the BCC iron. For FCC nickel, okay. Now we have also we don't have 12. I think we only have 6 configurations for the nickel. And then we also did it for this complex material, magnetic material. Iron HSP is the base for superconductor. Now you get a very complex spin configuration. So we did those ones. I want to show one example, 2 examples. One is for the iron 3 platinum. I mentioned iron 3 platinum in alloy. So this is some expansion plotted as a function of temperature at the ambient pressure. As you can see that the symbols are from experiments, the lines from the prediction of the model, all from DFT calculation without any models beyond the DFT. So what you see here is that the volume, some source increase, then maximize, then start decrease, become negative, then become minimum, then goes up again, right? That's the zero case. This is called inverse effect, was discovered in 1897. So then we can predict it. So how do we predict? As shown, we have this 512 configurations. We calculate the energy. We calculate the 37 unique ones. We calculate the total energy, EV curve. That's the first thing you do when you do the DFT calculations. And now you see a very important, interesting observation. The ground state volume is larger than the volumes of all other metastable configurations. It's important. It has to be metastable, not unstable ones. And now we have the free energy of all of them, 37 of them. You see that the red line shows is the reference state for the ferromagnetic. It's stable. It loses energy at all temperatures. That means if you look at the energy alone, there should be no transition. Nothing should happen. However, the difference between the blue ones, the metastable, and the stable ones is decreasing as temperature goes up. That means the probability of a metastable states increases when temperature goes up. Probability is not stable, but they have statistical probability. So we can calculate the probability of the different configurations, macrostate. The black line here is the ground state at this very low temperature, 100%. It's all ground state. However, when temperature increases, you can see that the non-ground states population starts to increase statistically. It reaches about 50%. So the ground state has low energy, free energy, but it only becomes 50% at certain temperature. If you increase them further, the ground state becomes less than 20%, even though it's still stable one from an energy point of view, free energy point of view. Okay. But the statistical mixing lowers the energy by increase the non-ground states or the metastable states to over 80%. So now we have each of these configurations have properties, right? They're predicted from DFT. So we can calculate phase diagram. They predict the phase diagram. The symbols again from experiments. The line is from the prediction. It's purely prediction now from DFT and predicted. And the red circle here is very important. Is a critical point. Critical point is where have divergence of the properties, the singularity. Now we get all the states. Then we can predict that what properties. We can calculate the magnetization. You can do you have now spin flipping. You can macroscopically. The magnetism becomes zero, even though individual ones are still magnetic. But over together, it's zero magnetization. And then you can also, now if you change the pressure to volume, you get this blue range here, which are negative sum expansion. That means there's a purple range. The lines are for different pressure. You put them together, you see there's a band here, which you get negative sum expansion. The reason is because there's a metastable states, their volumes are smaller than your ground state. Even though each of them has positive sum expansion, but then put together, the macroscopic volume could decrease at a certain pressure temperature range. Okay, so the one we just have one recent paper published. It's for electronucleate. Electronucleate is a very nasty, nasty is called a strong correlated material. The reason because the ship stage is big, okay, and it turned out again we do the ground state. When to the ground state, you find that half of the nickel is non-magnetic, okay, and half the nickel is magnetic. The nickel atoms actually become non-magnetic, half of them, so we can make the supercell much bigger. So we calculate again we first sample all the states, then we calculate their EV curve for all of them. Then we calculate the free energy. You got the same observation that the ground state is stable at all temperatures. Free energy lows at any temperature, you will consider from the experimental point of view to 300 Kelvin or even higher. So now we get to the stage, we mix them together. Use our Zentropy, use the free energy in the partition function. We predicted the 50% of the ground state at 144 Kelvin. The experimental transition temperature is 145 Kelvin. Now we get the total energy, free energy. We can take the standard statistic mechanics, right? So if we take the same calculations, but use the standard statistical mechanics, transition 81 Kelvin. Okay, so that's one of the reasons why we have all the tools, but our prediction is still off from experiment, right? So if you take this one, you take standard statistical mechanics, you find, oh, my temperature is way off from experiments. That's true for all the predictions. Most of the predictions we have today, when you use DFT, you do a prediction, oh, my temperature is off by 100 degrees. This is by 70 some degrees. Okay. Oh, 60 degrees. Oh, yeah, close to 70 degrees. And then you can talk about you can do all the TP diagram. You find that there are two transition temperatures and the 0 Kelvin, both are second order. Okay, and then merge together at 0 pressure, merge together at a high temperature. You can see you can predict the whole line of the second order transition between the AFM and the paramagnetic. So the question is that is this material really strong correlated? Okay, it is strong correlated, but in the supercell size we can handle. Beyond the supercell size, it's not strong correlated. It's purely statistical. And the statistical energy are determined by DFT with that 80 atom supercell. Okay, so 80 atoms is enough to cover this very complex three-dimensional properties, which you can measure from experiment. And we can also calculate the short range ordering for spin short range ordering. So take different states mixed together. If you're interested, I can send the paper to you because it's already accepted. Now, I have a friend from Department of Earth and Science for the ferroelectric materials. And you probably know that the Penn State is probably one of the best, or the best group doing the ferroelectric materials. Nothing against the Cambridge here. So they really do great work. So I'm a metallurgist. So when they talk to me, I didn't understand it. So then they showed me this diagram. This is the letter titanate, probably 1951. Plotted the lattice parameter as function of temperature by X-ray. Okay. Do I still have some time? Okay. So now what you see is that you see the top curve here is C-axis, and this is A-axis, right? So you see when temperature goes up, C decreases, A increases, and the transient temperature, they become equal, right? So that's pretty good. Then you say the tetrahedral goes to cubic transition. But if you put the volume together, you see that the volume of the tetragonal is here and decreasing, right? Decreasing. And then almost continuous. That's the argument here. If the volumes continues to change, what should be the order of the phase transition? Well, to me, it should be the second order. But the literature says first order. Okay. So I'm not going to argue that because I'm not an expert on ferroelectrics. Electric materials, but I say look at this diagram. I say it's first order, second order. But anyway, so what happens is that at low temperature you have the tetragonal, okay, and not only tetragonal, the central atom, which is titanium, also shift position. So you get a polarization. Okay, if you at a high temperature, if you do the measurements, you find you get a cubic. You find that the titanium atom is always in the center. So it has no macroscopic polarization. So of course, because those observations, you have to know the famous theory, Lennard theory, and they use this fitting. You got a curve that the polarization goes to 0 at a high temperature. Above this point, macroscopically polarization becomes 0. Okay. So Lennard theory explains that you fit the parameter, got a coefficient. People were using today those coefficients, right? As well, this coefficient was originally developed at Penn State by Professor Edgar Cross and his team in the 1970s. So these equations are widely used today to simulate phase transformation. Of course, we understand that's actually incorrect, the picture. Okay, microscopic picture is incorrect. The reason is because if you look at this paper by 1994, of course, there are many papers to show that. Again, this is CA lattice parameter plot. So the black lines are from the X-ray. Okay, that's actually before from the X-ray. But however, the symbols are from the X-sub measurements. What it does is that it measures the titanium atomic environment. Okay, then try to calculate the CA ratio locally for each titanium atom, basically, for the titanium edge. So you can see that the cross symbol here, from that submix, it doesn't change. The titanium locally is always tetragonal. You have C and A. So that paper was published in 1994, right? Of course, now you think this is only CA ratio, does not talk about the polarization, right? So you have to measure polarization too. The paper published polarization too. The polarization, if you do the, I think this one of them is X-ray. Let's see, one is neutron. I believe this is the neutron, right? Star. Let me just check that. Yeah, no, cross. The cross is X-ray, and this this is wow. This cross, that both are cross, one for neutron, one for scatter, X-ray. So it shows that at a transition temperature, they go to 0. That's right, no polarization. However, you look at individual titanium cell, the polarization stays at all temperature. Okay. It never disappears. So that means that the Landau theory is macroscopically correct, but microscopically incorrect. Did not represent reality, what the atom does. Okay. So then I thought, I got the ferroelectric work very magnetic, right? Then I said, I want to do the ferroelectric, see if our theory works. We struck for a long time, it didn't work. So then we said, then asked one of my postdocs, I said, can you do some simulation? We take AMD simulation, very important. Do ab initio molecular dynamics simulation without a fitting, okay, without a fitting parameter that gets potential. So now we do see that. So we take the white cubic is a cubic, CA ratio is cubic, okay? That means for X-ray, it does C and A. However, interesting is that you look at the blue ones are the titanium. You see the titanium atom moves up and move to the right, move down. So during the process, it crosses the central point. You get central symmetry, but it doesn't stay there. It goes over and then goes that way, right? Of course, we know that if this titanium goes up, that titanium goes down, what do I have between two? They cancel each other, overall cancel each other, that's right. So the macroscope is 0. But what about locally at the interface? So you create an interface between two cells, right? So you see, so if this one goes up, the other one goes down, that's what we call it. You have polarization up, polarization down. That's 180 domain, 180 degree domain wall, right? So of course that's very interesting. We write, that's fantastic. And the second is that if this one goes up, that one goes to the side. The one goes up, one goes away. What do you have? 90 degree domain wall. Of course, this one can go all direction, right? You can this direction, this direction, this direction, this direction. You have 4 directions for one of them. So then we thought that's interesting. So we'll look at it a bit further. We look at each titanium atom. We follow that and we see what it does like this first for a while, stay there for a while. And then after a while, decide, oh, maybe I should do like this. Okay. So that each titanium atom goes like this. And then after a while, it goes like that. And it goes like that. And the frequency of change switch is much higher at high temperature compared to low temperature. Let me say stay much longer time at one position. Okay. But the switch is very fast. Switch is instantaneous switch. Okay, almost instantaneous. All right, so we got that one worked out. That's 2015. Then we compare also the calculated CA ratio at each locally. We find that you see you have 3 lines here. The black lines, black dots and lines are from experiments, X-ray. The blue lines are from X-sub, also experiments. The red ones are from simulation, but it takes the experiment CA ratio for the macroscopic measurement. Okay, that one is a very low temperature. You can almost exactly match the experiment, right? Because at the time the most diagonal. But if your temperature goes up, you will see that the 2 lines diverges. Okay, and then this one maintained almost the same, doesn't change. A very nice agreement with experiment. So this simulation is purely DFT with molecular dynamics, okay, without a fitting there. And you can also look at the polarization. Again, the neutron, that's the green, and the X-ray black, and they all become 0. That's because it's overall. But locally, you have this experiment and the simulation. So then now the question is 2015. So why we still have not solved problem? That's still, as I mentioned to you, I'm not working on ferroelectrics. I don't really understand this kind of domain war stuff. Okay. So then 2 years ago, 3 years ago, just before the COVID, I got a visiting scholar And then suddenly we discussed it and realized that, gee, this domain walls are the beauty of the macrostates, right? So you have ferroelectric ones. Then you have all these kind of domain configurations. But turned out, of course, that people studied, right? So there's nothing new there, really. So if you calculate this 2002 paper, I think this is probably the first paper calculating domain wall energy by Professor Vanderbilt's group. Okay, so they calculate given the configuration, said these two are the stable ones. All other configurations are not stable. For example, if the two spin head to head is unstable, tail to tail is unstable. But you either have 180 degrees stable or 90 degrees stable. All other ones are not stable. That's good. So the calculated energy of these two. So then I thought, gee, now we have two states. Then we have three states, right? We have the purely ferromagnetic without domain walls. They have the 90 degree with domain walls, 180 degrees with domain walls. They calculate energy. So I tell my visiting scholar, I say, can you just take two energy and calculate it? So we get three states now, right? So we have ferromagnetic ground state, 90 degree domain wall, and 180 degree domain wall. 180 degree more energy is much higher than the 90 degree domain wall. So the probability of the 180 degree domain wall is almost zero. So most of them are 190 degree domain wall. And at around 776 Kelvin, and it becomes 50%. That means ground state is only 50% now, even it's lowest energy. Of course, you know, the experiment is 763, is 13 degree off. Right. So it's not exact. I think one of my reasons is that because we didn't use the free energy yet. Okay, so we need to get free energy to make it more accurate prediction. That's actually my new project, is to calculate free energy of this domain walls and put it back here. You can do that. All right, so that's what I hope Jack will be interested. We can take his materials and build up these microstates and do DFT calculation. So you can predict this transition can be one property. You actually predict all kinds of properties you can measure because it's all related to secondary derivatives of the free energy. The key is to get the free energy. As soon as you get the free energy, you can do derivatives, calculate all the properties you can measure. All right, so I'm finishing my talk. Oh, pretty good, 50 minutes. That's nice. So you want to read more? I have two papers showing up here. One in the 2020, or another 2022, which I've published. If I just summarize what we have here is that the entropy theory integrates the contributions to entropy starting from electron scale to the system scale by combining quantum mechanics and statistical mechanics. And based on the ergodicity of microstates, that's very important. It is demonstrated that the entropy theory is predictive without the additional models and the fitting of model parameters beyond DFT. So it's purely DFT based. Of course, you can question that DFT may have some problems too. Of course, it does, including the singularity at a critical point, with some expansion goes to infinite, positive and negative both. And we just got a new project on this one, really on Zentropy now. We're going to predict a number of properties. We're also looking for collaborations with any of you if you think you wanted to see what this model works for your system. Thank you very much.